Okay, because 1.25 million people die in car accidents every year, our team chose to tackle the problem of speed control for driverless cars because they promise to be safer. Starting with our model, we drew this force diagram, and from this force diagram we were able to find this mass damping system. And then from this mass damping system, we found this equation. Using Laplace transforms and basic algebra, we were able to transform this equation into this first order transfer function, which related velocity to the force on the vehicle. For our model, we chose to assume a pretty average mass for our vehicle of 1.5 thousand kilograms and a standard drag coefficient of 8.7 Newton seconds per meter. Cars don't drive just on flat road surfaces, sometimes there are inclines. We also wanted to focus on disturbances from inclines, which is represented in this model here.
Based on our transfer function, we can find the pole in the imaginary plane by pulling out the 1500. From this, we can find that the pole is located at 0.0058. This pole is located in the left half plane, indicating that it is stable. So when we put this model in Simulink, we found that the settling time was 20 seconds, which is very slow for our system. This requires a PI controller.
All right, so for our control system, we wanted to set certain metrics that we wanted to achieve. We wanted a settling time of less than or equal to 8 seconds, an overshoot of less than 7%, and a 0 steady state error. Our entire closed loop system is this, with Vn referencing the velocity N, our controller, which is a PI controller, our GFS, and our velocity out. We chose a PI controller for our CFS because the integrator will achieve 0 steady state, and we would need a proportional controller to speed up our system to achieve the settling time of 8 seconds. And so when we found the overall transfer function of our system, we found it to be T of S equals our KI plus KPS over MS squared plus parentheses B plus KPS plus KI. So in order for our system to remain stable, we need to find parameters for Ki and Kp, and we do that by doing the Routh array. So when we do the Routh array, we populate it with these values, and we result in this. So to find Ki using here, Ki needs to be greater than 0, and then using here, it's B plus Kp needs to be greater than 0, so Kp needs to be greater than negative B. So in order to find our Ki and Kp, we used our settling time specification of 8 seconds, and we found Ki equaling 1 and Kp equaling negative 7.55. When we simulated that in Simulink, it was very oscillatory, and so we needed to adjust our parameters for Ki and Kp. After we meddled with it for a little, we ended up getting Ki equaling 3,559.5 and Kp equaling 718.3.
All right, so as we verify our system, I've got the gains we chose for the integrator and the proportional component of our controller. The specifications we decided on were less than 8 seconds settling time, overshoot less than 7%, and a steady state error to our inputs of 0. So when we model it in Simulink, we get something like this, with a modeled input of 100 kilometers per hour. The settling time on our system with the controller achieves is 7.75, which is less than the 8-second settling time we wanted. The overshoot we have is 6%, which is less than the 7% we were hoping to achieve. And because of the use of an integrator, our steady state error to step inputs will be 0. After modeling our control system in Simulink and also using the CISO tool, we found our gain margin to be infinite, which means that we can have an infinitely increase the gain and our system will remain stable, which is good if there's any lurking gains or stuff we're not accounting for in our system. Additionally, we found the phase margin to be 85.3 degrees. And so what this allows for is for delays within our controller that will not result in unstable. This phase margin correlates to this equation, where Tmax is the maximum delay that our system can handle, where omega is the crossover frequency of our Bode plots. What we'll find out is that the max time delay that our system can take is 0.625 seconds, which is rather large, and we expect our controller to be able to handle. In conclusion, by using a PI controller, our system will be faster, it'll have 0 steady state error, manageable overshoot, and be within our settling time criteria.